You know, you probably tapped your phone screen, what, maybe 2,000 times today?
Oh, at least. Probably more, honestly.
Right. And every single one of those taps, like every swipe, every pinch to zoom you did, it relied on thousands of lines of logic.
Yeah, logic that was manually typed out by a human being.
Exactly. Sitting in a chair somewhere, just hammering away at a keyboard. But based on this exclusive leaked transcript we got from Apple's latest State of the Union, well, the era of humans acting as the bricklayers for our software, it is coming to a very abrupt end.
A somewhat violent end, really. I
Yeah.
mean, it is a complete structural dismantling of how software is built,
Yeah.
how it operates, and really how it interfaces with us. We are looking at a permanent shift away from apps as these static utility tools and moving towards software that is essentially a living, agentic environment.
Okay, let's unpack this. We are looking at a massive shift in how our devices operate, starting right at the core. And that is exactly what we are doing in today's deep dive. So welcome. If you're listening, we are thrilled to have you with us as we dissect this.
Yeah, this WWDC 26 Platform State of the Union leak is, well, for developers, it's the Holy Grail presentation.
Right. It's where Apple literally pops the hood on the new operating systems. But for you listening, we're not just going to read code updates.
No. We're dissecting the invisible architecture of your digital life.
Exactly. Our mission today is to decode all that heavy developer jargon and find those aha moments. We're going to figure out how the next generation of our devices will actually reason.
And how they'll organically connect our fragmented data.
Right. We're going to look at the brain, which is the AI foundation, then the nervous system, which is Siri connecting it all.
Then the skin, which is this wild new liquid glass design language.
Yeah, that part is crazy. And finally, we'll peek behind the curtain at the builders, meaning AI agents actually writing the code. But to understand any of that, we have to start at the foundational logic. Apple is fundamentally handing over the raw power of their Apple Intelligence Foundation models to, independent developers.
Handing over the raw materials, yes, but doing so within a highly constrained, highly engineered new paradigm.
Which is necessary, right?
Completely. What's fascinating here is the tension driving the entire tech industry right now. You have the sheer computational brute force required for these frontier AI models on one side.
Yeah, they need massive server farms.
Right. And then on the other side, the absolute necessity for user privacy. The transcript reveals Apple's hybrid architecture to solve this.
And it involves a surprisingly deep integration with Google's Gemini family of models, which, wait, I need to stop you right there.
I knew you would.
Because that immediately sets off alarm bells for me. I mean, Apple has spent the better part of a decade building a brand identity, fundamentally opposed to the data harvesting models of companies like Google.
What happens on your iPhone stays on your iPhone.
Exactly. So how does routing the most intimate, complex reasoning tasks of a user's life to a data-hungry search giant not completely obliterate that trust?
Well, it would. It absolutely would if the data were being handled through a traditional API structure.
Okay.
But Apple is circumventing the standard cloud model entirely here. They're routing these complex requests through their private cloud compute infrastructure.
Meaning what exactly?
Meaning they're treating the cloud not as a storage facility, but as a stateless, highly secure extension of the device's own internal processor.
Okay, define stateless for me in this context. Because the data still has to leave my phone, right, and travel to a server farm somewhere.
It does. But stateless means the server physically lacks the architectural capability to retain the data once the computation is finished.
Wait, really? Physically lacks the capability?
Yes. So imagine an app needs some heavy lifting done. Say you're analyzing a highly complex document. The phone encrypts the data, sends it to a private cloud compute node. That node decrypts the data inside a secure enclave. It performs the mathematical matrix multiplications using the Gemini-backed models, by the way.
Right, the math part.
It sends the output back to your phone.
Right.
And then, this is the key, the virtual machine image immediately wipes itself.
Wow.
The data is never written to persistent storage. It's actually cryptographically impossible for Apple, Google, or even a malicious actor to extract your personal context after the fact.
So it is essentially an amnesiac server.
That's a great way to put it.
It wakes up, solves the math problem you handed it, hands you the answer, and then immediately forgets you and the problem ever existed.
Precisely. And security researchers can actively audit the software images running on these servers to mathematically verify that zero data retention is occurring.
That's wild. But okay, the privacy engineering is rigorous, But reading further into this transcript, the economic implications are what really stuck out to me.
Oh, they are going to totally reorganize the software
Yeah,
industry.
because Apple is allowing developers with fewer than 2 million first-time App Store downloads to run these foundation models on private cloud compute for free.
Absolutely zero cloud API costs.
Which is, I mean, the unit economics of AI startups have been historically terrible because of those compute
Oh,
costs.
they're a nightmare.
Right. Like if you build a clever tool that summarizes PDFs and suddenly 1 million college students download it during finals week, you don't celebrate.
No, you panic. Because your AWS or OpenAI build just spiked to $50,000 overnight.
Exactly. So this financial friction has kept independent developers from deeply integrating AI into everyday utilities.
Right, because they couldn't afford it. But by absorbing the inference costs for the first 2 million users, Apple is effectively subsidizing the entire indie developer ecosystem.
That is massive.
It is. They're democratizing access to frontier intelligence. They're allowing a developer in their basement to build an app with the same reasoning capabilities as a heavily funded Silicon Valley incumbent.
I mean, 2 million downloads is an incredible runway to figure out your monetization strategy, but access to the models is really only half the battle, isn't it?
Very true. Wrangling large language models can be incredibly chaotic.
They hallucinate, they lose context, they get sluggish.
Yeah.
But the transcript details a specific sample app to show how this is going to work. It's called Origami.
A dedicated Japanese papercraft app.
Right, and it demonstrates how developers will actually orchestrate this intelligence using a mechanism called dynamic profiles.
And what's fascinating here is that dynamic profiles represent a huge leap forward in managing inference parameters locally.
How so?
Well, normally a developer sends a rigid prompt to an LLM, but user needs shift wildly from millisecond to millisecond, right? So the Origami app demonstrates a sequence where a user wants to combine a photo of their dog with a specific floral pattern paper to generate a custom folding project.
So for that initial ideation phase, you want the model to be highly creative. You want it making lateral leaps.
Exactly. So the developer taps into the private cloud compute model and dynamically cranks the sampling temperature up.
Okay, temperature. For those listening who might not be deep into AI parameters, a higher temperature basically flattens the probability distribution of the model's next token predictions, right?
Correct, which leads to more diverse, unconventional outputs. That profile acts as the, quote, brainstorming helper.
Right, but the moment the user selects a design and shifts to actually folding the paper, the application of intelligence has to fundamentally change.
Because if the AI starts hallucinating creative geometry during a tutorial,
You end up with a crumpled ball of paper.
exactly, you need precision. So the application seamlessly unloads that brainstorming profile and swaps to a tutorial generator profile.
So it's swapping personalities, basically.
In a way, yeah. Here, the developer forces a strict deterministic output by setting the reasoning parameters to prioritize spatial logic and physical constraints. They completely disable the high temperature variance.
Okay, that makes sense. But then the workflow introduces a third profile, right?
Yes. During the tutorial, the user encounters the term valley fold, and they tap it for an explanation.
And sending a request all the way to a cloud server just to define a basic origami term seems like a massive waste of energy and time.
It is a waste of latency. So instead of pinging the private cloud compute cluster, the dynamic profile instantly shifts the inference workload to a heavily quantized on-device language model.
A local jargon explainer.
Right, the definition generates instantly on the silicon in the user's hand. It reduces latency to 0 and saves cloud compute cycles.
But here's my question. If the app is constantly hot swapping between a creative cloud agent, a strict cloud logician, and a local dictionary, doesn't the user have to constantly re-explain what they're doing to each new instance?
That is the architectural brilliance of the new framework. The transcript notes that all three of these dynamic profiles share a single, unified, continuous context window.
Oh, wow.
Yeah. The local model running on the iPhone's neural engine doesn't wake up blank. It has full access to the KV cache, which is the stored memory of the interaction so far.
So it already knows the user is halfway through folding a dog out of floral paper.
Exactly. The intelligence is fragmented across different models and hardware locations to optimize speed and cost, but from the user's perspective, it feels like a single, omniscient entity anticipating their needs.
Okay, so the apps themselves are becoming hyper-aware, context-rich reasoning engines, but And this is a big but. Reasoning in a vacuum doesn't actually accomplish anything.
No, it doesn't.
If the AI can read the recipe but doesn't have hands to chop the vegetables, it's just a glorified text box.
That's a good analogy.
So how does Apple bridge the gap between this intelligence and the actual execution of tasks?
By fundamentally altering the role of Siri, we really have to strip away our preconceptions of Siri as this rudimentary voice assistant used to just set kitchen timers.
Yeah, or tell bad jokes.
Right. The State of the Union frames Siri's new architecture as a system-wide orchestrator. And the mechanisms powering this orchestration are the App Intents Framework and the Spotlight Semantic Index.
Okay, let's ground this in the mechanics so people can visualize it. In the origami sample, the user activates Siri generally, completely outside the app, and asks, "Who's coming to origami night?"
Now, in iOS 17, Siri would just enthusiastically offer you a series of useless web links about origami.
Here's what I found on the web.
Yeah.
Yeah, we all know that response.
But in the new architecture, Siri consults the local Spotlight Semantic Index. This index isn't just a list of files. It is a continuously updated on-device graph database of entities and relationships parsed from your applications.
So it's mapping the connections inside your apps.
Exactly. Siri queries the index, identifies the Origami app's internal messaging database, and reads the specific group chat. It replies contextually. Based on your messages in Origami, it looks like Kevin, Mary Beth, Rachel, and Richard are discussing Origami night.
And the user doesn't stop there. They follow up with, "What's Richard bringing?" They omit the context entirely.
Because Siri maintains the session state. It resolves the pronoun Richard, maps it to the specific entity in the Origami index, scans the relevant recent messages, and extracts the commitment. Richard mentioned he is thinking of bringing pizza.
Okay, and this leads to the critical action. The user says, "Siri, text Richard, can you make one of the pizzas vegetarian?" And Siri simply executes the command through the Messages app. The handoff between reading an indie app's database and writing an action to a core system app is completely frictionless.
Completely.
But surely the independent developer who built the Origami app didn't have to manually write thousands of lines of natural language processing code to anticipate every possible way a user might ask about pizza.
No, not at all. That is where the App Intents Framework acts as a universal API adapter. Apple has engineered standardized schemas for various software categories.
Schemas like what?
Schemas for task management, media playback, communication, photo editing. When the Origami developer builds their internal messaging feature, they simply tag the underlying code with the Apple-provided communication schema.
It's like they plug their specific plumbing into Apple's universal municipal water main.
Precisely. By adopting the schema, the app inherits Siri's entire semantic understanding layer. The developer doesn't write a single regular expression to parse user input.
So if the user says, "Text Richard," or "Shoot Richard a message," or "Tell Richard to make it vegetarian,"
Siri's massive underlying language model handles the linguistic variance. It distills the user's intent into a standardized JSON payload and hands that payload directly to the Origami app's functions.
and here's where it gets really interesting. If the language models update in the background, like if Siri suddenly learns a new regional dialect or a piece of modern slang tomorrow,
The independent developer's app instantly understands it without requiring an App Store update.
without changing a line of code, that is wild.
The intelligence layer is totally decoupled from the execution layer, and the transcript details an even more aggressive step toward contextual awareness. The View Annotations API.
Oh man, this part feels like it borders on science fiction.
It really does.
So the user is looking at a photo of a specific patterned paper on their screen inside the Origami app. They don't highlight it. They don't tap a share sheet. They literally just look at their phone and say, "Send this photo to Kevin."
That's the magic word.
Yeah.
To understand how this works mechanically, you have to understand how operating systems render graphics.
Okay, break it down.
Traditionally, the OS just sees a buffer of colored pixels. It doesn't intrinsically know that a cluster of green pixels represents a photo, while a cluster of black pixels represents text.
It's just light on a screen.
Right. But the View Annotations API allows developers to semantically tag the visual hierarchy of their UI.
So the developer explicitly tells the operating system, "This rectangle right here, at these coordinate planes, contains an image asset."
Yes. So when the user says the word "this," Siri captures the active screen state. It parses the View Annotations map provided by the developer, identifies the bounding box the user is currently focused on, extracts the underlying image asset, and pipes it directly into the communication schema we just discussed.
I have to play devil's advocate here,
Play
though.
for it.
Isn't this an absolute privacy nightmare? If Siri is constantly mapping my screen coordinates and reading the semantic layers of whatever I'm looking at, Apple is essentially building an automated, real-time surveillance engine right into the display compositor.
It is a profound security concern, which is why the mechanism of execution is strictly local.
Okay.
The semantic mapping and the screen buffer parsing do not happen in the private cloud compute layer.
Yeah.
They happen entirely on the local neural engine.
So it never leaves the phone.
Never. The OS creates a transient, localized representation of your screen state that is immediately flushed from memory the moment the intent is resolved. The system is aware of the context, but it does not broadcast the context.
Okay, so we have an architecture where the underlying logic is reasoning locally using dynamic models, and Siri is universally orchestrating actions by reading semantic schemas and mapping the visual UI hierarchy.
Yes.
But if Siri is doing all the heavy lifting of navigating the app, why does the UI even need to look the way it does? Like, if the software is radically adapting its function, how does it adapt its physical form?
If we connect this to the bigger picture, it's not just the intelligence that's adapting to the user. The visual interface itself is adapting dynamically to its environment. This leads directly to the physical appearance of iOS 27 and macOS 27, dominated by a new design language that Transcript refers to as liquid glass.
Liquid glass. I mean, software mimicking physical materials isn't new, right? We had skeuomorphism back in the day, we had flat design, we had basic translucency. But the specific mechanics detailed for liquid glass seem aggressively complex. They aren't just blurring a background image. They are calculating real-time light refraction.
They are actively simulating the physics of frosted glass dynamically laid over moving digital content. What's fascinating here is how the transcript details that liquid glass is tuned to diffuse complex layers behind it. They use a multi-pass rendering technique to establish depth.
Multipass meaning it renders the same frame multiple times to build up effects.
Exactly. First, the OS applies darkened edge strokes to create structural separation for the underlying window. Then, it calculates specular highlights.
Simulated glints of environmental light bouncing off the polished surface of the UI panel.
Right.
But weight rendering, layered, refracting light, and calculating specular highlights in real time across multiple floating windows. That sounds like a massive waste of GPU cycles just to make an app look pretty. How does the battery survive a constant real-time physics simulation running on top of every single interface element?
It requires an immense amount of compute overhead, you're right, which is why Apple had to tightly integrate the liquid glass rendering pipeline directly into the silicon architecture.
Ah, so it's hardware accelerated.
Deeply. The GPU on modern Apple silicon has dedicated hardware blocks optimized specifically for these kinds of compositing passes. It bypasses the standard rendering loop, allowing the hardware to calculate the refraction mathematics with minimal power draw. Furthermore, they are enforcing a strict visual harmony.
Yeah, the transcript was incredibly blunt about this. The old design is officially dead. Recompiling an app in Xcode 27 actively removes support for legacy window designs and forces the liquid glass standard automatically. They're literally burning the boats.
Because the environment is no longer static. You can't have rigid, opaque rectangles in an ecosystem built on fluidity. And this fluidity extends beyond just the texture of the material. It dictates the actual geometry of the applications through advanced responsive design.
It's like software acting like water. It takes the shape of whatever container you pour it into.
That's the perfect analogy.
Because the idea of designing a fixed rectangle for an iPhone screen is entirely obsolete. The transcript cites iPhone mirroring on the Mac as the catalyst that really breaks the paradigm.
Yes. An iOS app might be running on a 6-inch phone screen, but it might simultaneously be mirrored as a tiny floating widget on a Mac desktop or blown up to fill a 32-inch display.
Right. And to manage this infinite variance in aspect ratios, SwiftUI, which is the underlying framework for building these interfaces, is heavily leveraging algorithmic layouts rather than hard-coded dimensions.
The State of the Union gives a fascinating example of a toolbar handling responsive compression.
Oh, I loved this part. Because instead of writing separate code for a wide toolbar and a narrow toolbar, the developer assigns a visibility priority modifier to the buttons.
Correct. So if I build an app, I mathematically tag the share button as high priority and the archive button as low priority.
And then as the user physically resizes the liquid glass window, shrinking the horizontal axis, the SwiftUI engine recalculates the layout every single frame.
And when it runs out of physical pixels to display all the buttons, It doesn't throw an error or clip the text.
It looks at the priority modifiers, automatically pins the share button to the edge, gracefully animates the archive button out of existence, and tucks its functionality into a dynamically generated overflow menu.
The system mathematically handles the spatial degradation. The developer sets the rules of physics, and the UI behaves accordingly.
It's just so elegant.
And this structural adaptability is intrinsically linked to accessibility, which is huge. Often, complex visual designs like translucent refracting glass are absolute nightmares for users with visual impairments. It destroys contrast ratios.
Exactly. I was wondering how a visually impaired user navigates a multi-layered, specular highlighted translucent interface.
The brilliance of the liquid glass material is that it natively hooks into the OS-level accessibility demons. If a user toggles reduced transparency or increased contrast in their system settings, the developer doesn't have to trigger an alternative UI block. The underlying mathematics of the liquid glass shader instantly adapt. The alpha channels are overridden, the diffusion parameters are hardened, and the material physically changes its properties to ensure legibility.
Without the developer writing a single line of compliance code.
Exactly.
It's reactive architecture. But, the most jarring visual leap in the transcript wasn't about flat windows on a screen. It was about moving the UI entirely off the 2D plane and manipulating the Z-axis using the new spatial preview framework for Apple Vision Pro.
This is where macOS fundamentally intersects with spatial computing. Currently, when you use a Mac inside a Vision Pro headset, the Mac's screen appears as a massive, flat, 2D billboard hovering in your physical room.
Just a floating TV, basically.
Right. But the spatial preview framework shatters that 2D boundary. The transcript details an API that allows Mac applications to extend 3D objects out of the flat billboard and push them into the volumetric space of the user's living room.
Mechanically, how does that even work?
The Mac application passes a USDZ file, a specialized 3D format, through the OS compositor, which hands the spatial coordinates off to the Vision Pro's rendering engine.
So you could be looking at a standard 2D web page about a jet engine on your virtual Mac screen, but the 3D model of the engine physically protrudes from the screen.
Yes, hovering over your physical keyboard, reacting to the ambient lighting of your actual room.
Okay, but listen, all these adaptive graphics, layered glass, and AI models running at once. Wouldn't that just melt a standard computer? How is this actually running smoothly? We have AI models reasoning across multiple contexts, Siri parsing semantic buffers, real-time physics calculating light refraction, and OS compositors pushing spatial geometries into augmented reality. That is an absurd computational load. There is a physical limit to how many electrons you can push through a chip.
There is. And to achieve this, Apple had to execute a brutal architectural purge.
A purge.
The transcript confirms that macOS Tahoe was the final release to support Intel hardware. The ecosystem has officially severed the umbilical cord of the past. It is now 100% Apple Silicon.
For you listening, the transition to Apple Silicon has been happening for years. But what does the total 100% cutoff actually unlock under the hood? Apple is basically doing a total renovation of the house while we are still looking inside it.
Well, when an operating system has to support two wildly different CPU architectures, Intel's x86 architecture and Apple's ARM-based silicon, the system must carry an immense amount of translation layers, redundancies, and compromises. Developers have had to ship universal binaries, essentially packing two massive, distinct versions of their compiled code into a single download.
A bloated package just in case it lands on a 6-year-old laptop.
Precisely. By enforcing the cutoff, developers are now shipping purely optimized Apple Silicon binaries. The application payloads are physically smaller, they decompress and load into memory significantly faster, and the operating system itself can jettison millions of lines of legacy compatibility code.
The engine is vastly lighter.
But shedding Intel is only the first step. The transcript reveals a much deeper structural renovation involving the Swift programming language itself.
This part of the document genuinely surprised me. Most people associate Swift purely with UI development. It's the friendly language you use to build an iPhone app. But Apple is aggressively pushing Swift down into the most foundational, low-level plumbing of the system. They are actively replacing code that has been running for decades in C and C++ would.
And that transition is critical for security and performance. C and C++ are incredibly fast, which is why operating systems rely on them, but they demand manual memory management. They are completely devoid of inherent memory safety.
Let's break down that mechanism. What does lack of memory safety actually mean in a C++ environment?
Okay, so in C++, a developer uses pointers. A pointer is essentially a raw memory address. If the program allocates a block of memory to store an image and later deletes that image but forgets to securely erase the pointer, you have what's called a dangling pointer.
The program still thinks there is valid data at that address.
Right. And if a hacker recognizes this vulnerability, they can strategically write malicious execution code into that abandoned memory address. When the program inevitably accesses the dangling pointer, it inadvertently executes the hacker's payload. This is how the vast majority of catastrophic security breaches and system crashes occur.
It's like leaving the physical key to a bank vault taped to the front door after you've emptied the vault, hoping nobody tries to open it and put something dangerous inside.
Exactly. And Swift completely eliminates this entire class of vulnerabilities at the compiler level. Swift uses automatic reference counting and strict bounds checking. It mathematically tracks the life cycle of every object in memory.
So if an object is no longer needed,
The system automatically deallocates the memory and destroys the references. You cannot have a dangling pointer in Swift. It simply will not compile.
and traditionally, languages with that level of automated safety suffered from massive performance overhead. But Swift has evolved to the point where it is matching, or in some cases beating, bare metal C++ speeds.
Which gave Apple the confidence to execute the examples listed in the transcript. They rewrote the core networking transport components of WebKit, the engine that powers Safari entirely in Swift.
And the web browser is arguably the single most targeted attack vector on a modern computer. Moving its lowest level networking protocols away from C++ and into a memory-safe language is a massive infrastructural hardening.
Huge. They also replaced the TrueType font rendering engine. This is a module previously written in heavily hand-optimized, decades-old C code. Every single glyph on every single interface, thousands of times a second, passes through this engine.
Yeah, if you introduce even a microsecond of latency into font rendering, the entire operating system feels sluggish. The fact that Swift handles this flawlessly proves its raw speed. They even casually mention that portions of the Core OS kernel, the absolute bedrock orchestrator of the hardware, are now written in Swift.
But Swift's dominion isn't just expanding downward into the kernel, it's expanding horizontally across the entire industry. This was a detail that deserved a lot more attention in the transcript. They highlighted GoodNotes reusing 100,000 lines of Swift code to bring their app to the web, Android, and Windows, completely bypassing JavaScript, using something called WebAssembly.
WebAssembly, okay, WASM.
Yeah, WASM is a fundamental threat to the current paradigm of web development. For decades, if you wanted code to run in a web browser, it generally had to be written in JavaScript or TypeScript. The browser's engine would parse that script and execute it.
Which is incredibly inefficient and slow compared to a native app.
WebAssembly changes the rules. It is a low-level binary format that runs inside a highly optimized virtual machine within the browser. GoodNotes didn't rewrite their app in JavaScript for the web. They took their incredibly fast, memory-safe Swift code, compiled it directly into a WebAssembly binary, and pushed it to the browser.
It executes at near-native speeds, interacting directly with the browser's APIs.
Right. This essentially means a developer can write high-performance logic once, in Swift, and deploy it literally everywhere, from a Vision Pro headset to a Windows desktop to a generic web browser. They also mentioned the flight tracking app Flighty running Swift on their back-end Linux servers. They are unifying the entire stack under one language.
But standardizing on one language means the compiler for that language has to handle an astronomical level of complexity. Which brings us to the compiler diagnostic updates mentioned in Swift 6.4.
Oh, I have to admit, as someone who spends their life looking at system architecture, this specific fix solves one of the most infuriating bottlenecks in modern software development.
You were talking about the dreaded error message. The compiler is unable to type check this expression in reasonable time. Walk me through the mechanics of why the Swift compiler was essentially having a panic attack and refusing to build the code.
It comes back to the fluid, responsive interfaces we discussed earlier. In Swift UI, developers nest layouts inside of layouts inside of layouts. A horizontal stack of buttons inside a vertical stack of content inside a responsive liquid glass window. Because SwiftUI relies heavily on type inference, meaning the compiler has to figure out the exact data type of every variable on the fly, the mathematical combinations become exponential.
So the compiler starts calculating. If the window is this wide, the button is this big, which means the text wraps like this, which means the parent container must expand like this.
Yes, and it tries to calculate the validity of every possible permutation across the entire nested tree simultaneously. When the algorithmic complexity exceeded a hard-coded time limit, the compiler simply aborted the process and threw that reasonable time error. It forced developers to manually break their elegant code into disjointed fragments just to spoon-feed it to the compiler.
How does Swift 6.4 solve it? They didn't just increase the timeout limit, right?
No, they implemented heuristic short-circuiting. The Swift 6.4 compiler's type checker now analyzes the dependency graph of the UI elements. If it determines that the size of a child element cannot physically alter the constraints of a parent element in a specific dimension, it cleanly snips that branch of the computational tree. It stops calculating permutations that don't matter.
And the practical outcome of this optimization is staggering. The transcript notes that layouts now resize up to twice as fast. When you grab the corner of a complex application window and drag it across your screen, the app has to repaint the entire liquid glass UI at 60 or 120 frames a second. By short-circuiting the underlying layout calculations, the system avoids dropping frames, resulting in completely fluid resizing without stuttering.
The plumbing is flawless. The memory is safe. The rendering is instantaneous. But this raises an important question. If the code is getting this complex, how are human developers keeping up? This escalating architectural perfection creates a paradox.
Exactly. The code spanning from the web server down to the bare metal kernel, the spatial algorithms manipulating 3D coordinates, the dynamic profiling of AI inference parameters, the sheer cognitive load of understanding all these intersecting systems is surpassing human capacity. How does a single developer, or even a highly funded engineering team, maintain this architecture without collapsing under the complexity?
The stark reality presented in the final section of the State of the Union is that human developers are no longer expected to manage the micro-complexity. We are shifting from humans writing logic to AI agents orchestrating architecture.
This brings us to the most disruptive reveal of the entire deep dive. Xcode 27 and the integration of deep agentic coding. And to be clear, we are no longer talking about AI features inside the apps we use. We are talking about autonomous AI agents actively writing, testing, and deploying the apps.
Right. To set the baseline, Xcode is Apple's primary integrated development environment. It's the central nervous system for writing Apple software. The transcript notes some quality of life improvements. It's 30% smaller, it utilizes iCloud to sync configurations across workstations, and it features highly engineered visual themes like neon noir, emerald, electric, and coral reef, which subtly optimize contrast to reduce cognitive fatigue during long sessions.
All nice updates, but the true paradigm shift is the workflow demonstration they provided. Let's look at how the Origami app developer supposedly adds a new complex feature using Xcode 27. The goal is to build a choose-your-own-adventure story generator based on the origami figures a user has folded.
In the past, the developer would begin by manually defining variables, laying out structural views, writing the networking code to call an LLM, and handling the error states. In Xcode 27, the developer opens an inline command window and simply prompts the environment in natural language describing the desired feature.
But they don't ask the AI to just spit out code. The transcript highlights a specific command parameter, /PL.
The plan parameter. This is a critical distinction between a basic code completion tool and an agentic workflow. When invoked with /PL, the agent analyzes the prompt and outputs a comprehensive markdown document detailing the architectural blueprint.
Because reviewing a high-level schematic is exponentially faster and safer for a human than reviewing raw, uncompiled logic.
Exactly. And the agent doesn't generate this plan in a vacuum. It parses the entire existing origami codebase. It maps the data models, understands the current UI paradigms, and recognizes dependencies. It even identifies ambiguities in the developer's prompt and actively asks clarifying questions.
Really? Like what?
The transcript shows the agent asking, do you want to persist these stories? Meaning, do you want to write the database schema to save this data to the local disk, or is this a transient session?
The developer responds, confirms they want persistence, dictates some UI constraints, and approves the markdown plan. Then, and only then, the agent autonomously executes the implementation, writing the Swift UI views, linking the dynamic profiles, and configuring the data models. The code is written, but writing code is cheap. Testing code is the real bottleneck, and this is where the demonstration crosses into the surreal.
Once the code is compiled, the agent initializes the new device hub.
The transcript describes Device Hub as a high-fidelity evolution of the traditional software simulator. It doesn't just display pixels, it simulates the hardware environment, including complex multi-touch interactions like pinch-to-zoom.
What happens next is a fundamental automation of quality assurance. The AI agent that wrote the code launches the compiled app inside the device hub, and it essentially possesses the simulator. Using computer vision, it scans the UI it just created, it maps the interactive elements, and it simulates physical human interaction.
Wait, the AI is writing the code, building the interface, A&D pretending to be a human tapping the screen to test it.
Yes, it literally taps the screen, it swipes it, inputs text. The AI acts as its own beta tester, navigating through the choose-your-own-adventure flow, validating that the buttons trigger the correct state changes. It tests the application in dark mode, light mode, and across different dynamic type sizes to ensure the liquid glass layout doesn't break.
And while running these automated visual tests, it simultaneously identifies string files and uses its contextual awareness of the surrounding codebase to execute a localized French translation of the new feature. Not a literal dictionary translation, but a semantically accurate localization based on the context of Japanese papercraft. What is the human developer even doing at this point?
Finally, the agent aggregates all of this, the visual layouts, the test results, the translation mapping into a summary report, complete with screenshots of the various edge cases, and presents it to the human developer. The human developer is completely removed from the execution loop. They operate entirely in the orchestration loop.
I have to challenge this model, though. If an AI is generating the code, parsing the layout, testing the interactions, and writing the localizations, the human developer is essentially just an editor at this point. Doesn't this completely hollow out the profession of software engineering?
It hollows out the rote mechanics of coding, but it dramatically elevates the cognitive requirements of system design. The transcript introduces the Agent Client Protocol, or ACP, which proves Apple isn't trying to monopolize the intelligence.
Right. ACP is an open standard. Developers can paste a Git URL and bring in their own agents from Figma turning designs straight to Swift UI or from GitHub, Anthropic, or OpenAI.
This is a profound architectural decision. You can import specialized agents fine-tuned on a company's proprietary code base. It's not replacing the developer, it's elevating them from a bricklayer to an architect.
The architect doesn't pour the concrete. The architect determines how the building should flow, how it interacts with the environment, and what human problems it solves.
And crucially, the architect ensures the building doesn't collapse under load. Even AI-generated code will encounter unpredictable edge cases when deployed to millions of real-world users. Look at how the transcript details the new organizer tool in Xcode 27.
Historically, the organizer is where developers go to look at crash logs. Massive, cryptic stack traces submitted automatically when an app dies on a user's phone. Figuring out which specific line of code out of a million caused a memory leak is a nightmare.
In the new paradigm, an AI agent continuously monitors the anonymized crash reports. When it detects an anomaly, it doesn't just flag it for the human.
Let me guess, it fixes it.
It reads the stack trace, cross-references it with the codebase, pinpoints the specific line of code that caused the crash, synthesizes the patch, reproduces the crash locally in the device hub to verify the fix works, and submits a pull request with the patched code.
The agent finds the leak, plumbs the new pipe, tests the water pressure, and asks the human to sign off on the invoice. The friction of maintaining a complex application is dropping asymptotically to zero.
It is the realization of software as a self-healing living organism.
What an incredible trajectory to map out. Let's zoom out and look at the entirety of the architecture we've unpacked from this transcript. AI models running on device for free, Siri orchestrating apps like a digital maestro, liquid glass interfaces, and AI agents writing code.
We observed a complete top-to-bottom rewrite of the digital ecosystem. It starts with democratized, on-device reasoning, utilizing dynamic profiles that fluidly adjust inference parameters while maintaining a continuous context window backed by the stateless, cryptographically secure, private cloud compute architecture.
We saw how that localized intelligence is granted agency through Siri, which has evolved from a voice assistant into a universal system orchestrator. Siri reads local semantic indexes and utilizes the View Annotations API to map visual screen coordinates, piping user intent through standardized app intent schemas to seamlessly control third-party applications.
We explored how the physical properties of the interface are reacting to this fluid intelligence. The mandate of liquid glass requires real-time algorithmic rendering of light refraction and depth, forcing developers to abandon fixed layouts in favor of SwiftUI's mathematically responsive priority modifiers. And we saw this fluidity extend into augmented reality, with the spatial preview framework pushing 2D bounds into the z-axis.
All of this is underpinned by the ruthless transition to a purely Apple silicon architecture, running deeply optimized, memory-safe, Swift 6.4 code that scales from the bare metal OS kernel all the way out to WebAssembly binaries running in web browsers.
And finally, we confronted the reality that the sheer density of this architecture necessitates agentic coding. Open standard AI agents within Xcode 27 are now fundamentally responsible for the generation, visual testing, localization, and automated patching of the codebase, elevating the human developer into a purely orchestrating architectural role.
It changes everything. Whether you are a senior software engineer managing massive server deployments or just someone who uses a smartphone to order a coffee and text a friend, this represents a fundamental shift. Our apps are becoming living, adaptable entities.
The architecture is no longer static. It is actively sensing, reasoning, and reshaping itself around your context in real time. The barriers between intent and execution have effectively been eliminated.
And as we close out, that realization leaves me with one highly provocative structural paradox to chew on. We just spent the last hour dissecting how autonomous AI agents in Xcode are now generating the software, building the intricate liquid glass interfaces, and writing the logic. Simultaneously, we discussed how Apple Intelligence agents, via Siri's semantic orchestration, are increasingly the entities actually interacting with those apps for us. Siri, text Richard. Siri, summarize this document. Siri, extract the photo.
The agentic loop is closing in on itself.
Precisely. The machine is writing the software, and the machine is increasingly navigating the software. So how long until we have AI making software specifically for other AI to use, bypassing human visual design entirely? If a human eye is rarely required to physically open the app, navigate the menus, or read the text, why are we wasting massive amounts of GPU compute simulating refracting liquid glass and calculating specular highlights? At what point does the visual interface completely dissolve into an invisible exchange of API payloads, rendering human-centric design entirely obsolete? Something to think about next time you tap an app icon.
A phenomenal architectural question that strikes at the core of human-computer interaction.
Well, keep questioning the framework, and we will catch you on the next deep dive.